All right, all you cats and kittens, we're here to study for our physics. And you want to know that physics is the way things work. It deals with energy, matter, deals with everything in the universe and how it interacts. But the short answer is it's how things work. You guys use math as a tool to understand, but also communicate physics concepts. That way, we're all on the same page. And in the third question, talking about an organized process of steps that's used to find answers to questions about the world. That's a method. It's a scientific method. Scientific method is just a process. The information that you gather in the fourth question, you can refer to as data. Data is quantitative, meaning it deals with numbers. Qualitative observations would be like the smell, the color, the taste. Quantitative would be the speed, the distance, the time. Now, a good hypothesis studies a relationship that explains the cause and the effect. So some characteristics of a good hypothesis would be, obviously, it's repeatable, but it has to be reliable. It has to have a cause and effect relationship. And another good way is to be like, if you want to say cause and effect, you say an if-then relationship. But it has to have variables, independent, dependent, and controlled. A control variable in the experiment, it's a constant that doesn't change. Experiment, you really only want to test one variable at a time. So if you're studying the effects of fertilizer on a plant, you don't want to also change the soil, you don't want to change the light, you want all those things to be controlled. So keep that in mind. A control variable helps the possibility of other variables not be counted. And another important variable is the independent variable. In question 8, talks about the job of the independent variable. The job of the independent variable is to determine the cause. It's the cause of what gets affected. It's the cause of the effect. All right, so we talked about the job of the independent variable. The independent variable can cause a change in the dependent, but the dependent can never cause a change in the independent. So the independent can cause a change in the dependent. However, the dependent can never cause a change. It's impossible for the dependent to cause a change in the independent. SI units are pretty important because we do use math to communicate. We have a lot of equations. SI units for mass are going to be kilograms. It's a little different in physics than, say, chemistry. You're probably used to using grams a lot. We want to use kilograms for our SI units. They work with all of our equations and formulas. So if a student wanted to measure how far she walked around the school, the SI unit for the length or the distance would be in meters. There's a difference between types of measurements. Some are vectors, some are scalars. Vectors are quantities that contain both direction and magnitude. Oh, yeah. All right, so we should move on here in number 14. Oh, we did skip 13. Okay, so 12 vectors are quantities at magnitude, direction. 13 distance and speed. Distance and speed, since they have no direction, those have to be scalars. Time is a scalar. Something like volume is a scalar. You wouldn't say it's 5 o'clock to the north. So think of scalars as not having direction. In number 14, there is an SI unit that measures temperature. We're using kelvins, capital K, named after the Lord Kelvin. But enough on that. Control variables do what to the experiment? We already mentioned how control variables help keep the experiment consistent. And the independent variable is always graphed on the X. The independent variable changes what's happening to the experiment. Now in the diagram below, it's 17, 18, 19 is very helpful. You've got a plane that's moving and you've got a kite that's moving. Nothing else is moving. The guy is standing still, the building's still, the tree is still. So in number 17, it says, which frame of reference do you think would show the plane moving? Well, according to all of those other frames of references, the plane does look like it's moving. So anything but the plane would make it look like it's moving. All of them would make it look like the plane is moving. The tree would think the plane is moving. The kite would think the person would think the plane is moving. And at 18, from what frame of reference does the tree to look to or appear to be moving? It's none of them, except if you're on the plane or if you're on the kite. Because the plane and the kite could be moving, and it'll make everything else look like it's moving. And number 19, what frame of reference does the kite appear to move? All of them, because the kite itself is actually moving. Unless you were literally on the kite, you wouldn't think that you were moving. Okay, we'll flip it over to the next section here. 20 through 29 deals with distance and displacement and position time graphs. Now, distance is the length of the path between the 2 points. Displacement is the distance with direction. How are they similar? They both use the same units. They're both going to use meters, but displacement is going to be like saying from point A to point B. They're so different because displacement measures the change in position. Okay, so if you look at vector value would be displacement. It deals with direction and position. If you look at 22, the whole distance is the wiggly line of the race, but displacement would be from point A to point B, from literally where you started to where you finished. You do have some formulas on here for average speed. Speed is distance over time. Speed is a scalar. It doesn't need displacement. And you should be able to manipulate that formula too. So distance would be speed times time, for example. So the best tool for measuring instantaneous speed, remember instantaneous speed is not average speed. It's the speed at that very moment. Use a speedometer. You look right down at the speedometer at that very instant that tells you your speed. If you were looking at your Maps app or your GPS, you would have to be taking a total trip average. You'd be taking the average speed, not instantaneous. And number 26, we ask, is velocity a vector or a scalar? Velocity contains direction, so what would it be, guys? That would be a vector. Good answer. In 27, it asks, why is velocity different than speed? Well, duh, velocity is a vector, so I'm kind of asking you the same thing. It relies on direction, or indicates or contains direction. Velocity contains direction. So you could have positive velocity and negative velocity. You can't have that with speed. The abbreviation for average velocity, meters per second, or if you see a little v with an average subscript, you're going to know that that means average velocity. The graphs of motion are a pretty cool way of understanding which one's speeding up, slowing down, or standing still. It tells you the answer if you read the words in here. This number one, the steeper the slope, the faster the motion, or the higher the speed. So the first one has no slope. Position versus time is a straight line. There is no velocity. It's standing still. In the second one, you have a very constant slope, and it's positive. It's going upward. So that means your position is moving away from the origin, but at a steady rate. So at a steady rate of change, that's constant velocity. The second one is going in a negative direction, but also at a constant rate. You'll see it's linear, just like the one before it. Look for the clues when you have curved lines. The very last one that has a curve tells you that yes, it is accelerating. Acceleration deals with uh, change in velocity over change in time. So it involves a direction. In this case, it's a positive acceleration because the curve is going upwards. But the velocity is changing. The speed component is changing. Okay. Key terms you need to know about acceleration. First of all, acceleration, this is on the next page. Acceleration is going to be the change in displacement over time. Vectors contain direction and magnitude. Constant acceleration is when objects are accelerating, but that rate stays the same. So regular old definition is a change in velocity over time for acceleration. Acceleration is a vector because it contains magnitude and direction. And when you have constant acceleration, think of little g. Acceleration due to gravity never changes. It's always a constant 10 meters per second squared. Why is acceleration a vector? Because not only does it take into account changes in speed, it also takes into account changes of direction. So for example, you could be stopping, but you could be speeding up, but you could also be turning. A left turn or a right turn or going around a corner, that's an acceleration, even if your speed were the same. So look at the clues on these graphs when you have position versus time. The one that's accelerating would always have a curvature to it because that's going to show you a slope that's not constant. So a curved slope is going to always show you an accelerating object on a position versus time graph. So you can study those below, and then we'll ask you in 34 to identify which ones are accelerating. So the only ones that have curvature to them, which should stand out to you, would be letter C, letter D, and letter E. Now A has pretty straight slope, B has a very straight slope. So that should stand out to you right away. Look for a curvature of a position time graph when you're trying to find acceleration. And we're back. In number 34, they ask you which of the following are vector quantities. I literally like cross off the ones that aren't, and I circle or underline the ones that are. Velocity is a vector. Speed is not. Width is not. Displacement is. So all you have on that is I and IV, or 2 and 4. Select letter D for that answer. And the second one, I apologize, it cut the page off when it said which of the following groups are vectors. On your paper, you're going to have to turn it over. The ones that are vectors, velocity is a vector, displacement is a vector, speed is not. So it's not A. B, time is not a vector. Acceleration is, speed is not. Acceleration in C is. Velocity in C is. Displacement in letter C is. So C makes like the best choice because they all are vectors. In letter D, time is not, distance is not, but acceleration is. So we look, it's pretty obvious. It's letter C. And the third question, the length of the arrow tells you the magnitude. Which way it's pointing will tell you the direction. So you can literally compare vector sizes based on their arrows. And you know that resultants are made up of components. And we use the parallelogram method to find the resultant vector. It's not only the magnitude, it's not only the direction, and scalar of the vector is like a non-answer. We use the parallelogram method to find the resultant vector. Now, the next three here are some word problems and you want to look at distance, displacement in the airplane problem. If you're going to the east at 350 kilometers per hour and then the wind is hitting you to the west, the directions are opposite. The directions are opposite, so you can't add them, you subtract them. So the final velocity is 350 minus 50. It's giving you 300 to the east. Now, if you're ever at the airport and you get on those people movers, it looks like the Jetsons, that thing that you stand on, and it adds velocity to you. It gives you more speed in the same direction. So maybe my walking speed is 1.4 meters per second, but if I get on the moving walkway and that adds 2 meters per second, I can combine those together to get 3.4 meters per second. The gecko on the tree seemed to be a point of confusion for a lot of us, so we'll go over that in just a sec. I drew a picture for the gecko. I started him out at 20 meters. He's already positive 20 meters off the ground. And I showed his path going up to 60 meters. Now, the last movement he does is he goes down to the 50-meter line. But the question is, what's his total displacement? So take point A to B, or start to finish, and look at the difference in those values. Your final minus your initial in that case is 50 minus 20. So it's simply 30 meters for his displacement in that one. We said that the parallelogram method is a way to find the resultant vectors. It can also be used backwards to find the component vectors. So let's first try to find resultant vectors by drawing a picture. All you need to do is create a parallelogram, meaning you make lines parallel to the lines that were given to you. So you make the top line parallel to the bottom line, the side line parallel to the side line, and you have to draw your resultant from the base of the components. So where the tails of the components meet in this method, you want to start the tail of your resultant, and you want to end it where the next corner of the parallelogram ends. Don't be thrown off with angled ones like the 3 on the bottom. Okay, guys, we're going to look at the opposite operation of creating the resultant vector. We're going to find the components. So in this case, you are given the resultant, and it has an arrow with a magnitude and a direction, and we're using a grid line in the x and y components to show you which way the vectors go. You're limited by the magnitude of your resultant. Your components can only be as large as the resultant is. So simply draw a line on the x for the x resultant, x component, and draw a line up and down in the y for the y component. And this holds true for all of our examples. It's like the reverse of the parallelogram method. All right, this page is pretty interesting because we take some words and we fill in the blank, but I really want you guys to understand this. Say an elephant was charging and a moose was charging. They're going to have different masses. They're going to have different effects. but if an elephant and a moose have a weight of 0 newtons way out in outer space, they're free of gravity, they're free of friction. Would they retain their amount of matter or their mass? You bet, Red Rider. If they were moving towards you with the same speed, would they bump into you with the same effect? Well, no. So their mass is constant, but their inertia is greater based on their mass. So an elephant has more mass, elephant has more inertia. Think of mass and inertia, or mass as a measurement of inertia. So the law of inertia states that there is no force required to maintain motion. Just like if they were given a push in space, they're far away from gravity, they wouldn't need anything to keep them going. So why do I have to keep pedaling my bicycle? Well, that's because I'm always fighting the friction of the road, and I'm fighting air resistance. Friction opposes motion. That's the key concept to that one. Friction opposes motion. So you have to just keep pedaling to keep moving because you're always fighting friction. And the third one, we talk about automobile passengers. This deals with the injury called whiplash. And in Newton's first law, you have a mass, your head. Your head is heavy. You know, they say some people, you know, with big brains like me, they could have a 20-pound head. I don't know about you guys. You can put your head on a scale and see. You want to pivot weights like that. Your neck acts like a pivot point. So the mass of your head wants to keep going forward when the car keeps going forward, and then when it comes to a stop, your head's going to jerk back. So a headrest can help prevent whiplash because it will block the large mass of your head from whipping back and forth. When your head whips back and forth, I heard a song like that once. I whip my head back and forth. I whip my head back and forth. Anyway, when your head whips back and forth, you get whiplash. The seat headrest stops the whiplash. Let's say you're on a plane and the plane's going 600 kilometers per hour. Well, you are going 600 kilometers per hour too because you're on the plane. The pillow in the plane is going 600 kilometers per hour. The luggage in the overhead compartment is going 600 kilometers per hour. It's all like a system. So if the pillow fell from the overhead compartment, it's not going to suddenly fly backwards because it's already going 600 kilometers per hour. This is Newton's first law. This is the pillow has inertia. It wants to keep moving at the same speed and direction that it already has been going. My favorite question is about the elephant. The elephant is chasing you. If you zigzag, you can juke him. You can shake the elephant because he has such a greater mass. He has greater inertia. That's why that would be to your advantage. More mass equals more inertia. All right, our final question on this page talks about a probe. They give you a mass of 1,000 kilograms, and they give you a time of 1,000 years. So if you're in a spaceship and they fired a probe into frictionless space, yes, it would go for 1,000 years or more until it encountered another force. So there was no outside force acting on it. It wanted to keep going. These are some interesting questions about Newton's first law that I thought would be fun to include. Again, an astronaut way out in space, if they throw a rock, there's no friction, so it needs to continually move in a straight line at a constant speed. The rock's tendency obviously is called inertia, but look at this example number 2 where someone is spinning a rock over their head like on a string. If you cut the string at that point, the direction stays the same. It stays going in the C direction. There is no tendency for it to keep a circular direction unless a force was acting on it. Once you get rid of that string tension force, it's free to move in the same direction it would be going if you were just to let it go. important because weight is a force, mass is a amount of measure in an object. Mass, we use kilograms. Weight, we're going to use newtons because it's a force. Now, the basic formula, F equals ma, comes from Newton's second law. To apply that to weight, you would take weight equals mass times acceleration due to gravity. So that answer for weight's always going to be newtons. Acceleration of gravity is going to be based on where you are. So on Earth, it's always 10. But look over here, there's a key of important values. On Mars, little g is going to be 4. And on Jupiter, it's 27. So on Earth, what's the mass? Well, they gave you a mass of 83 kilograms, so her mass on Earth stays 83. It's always 83. Mass never changes no matter where you are. The weight, though, you're going to have to multiply the mass of 83 kilograms times the acceleration of 10 meters per second squared. You're going to get 830 newtons. Obviously, you're going to weigh different on Mars. On Mars, the acceleration due to gravity is 4 meters per second. So you're going to take your 83 kilogram mass, multiply it by 4 meters per second. Your answer is going to be in newtons. And if we put it in our calculator, 83 times 4 gives us 332 newtons. Does the mass change when you go to Mars? No, sir or ma'am. The mass is always going to be 83 kilograms. So apparently girls also go to Jupiter, and she went to Jupiter with a mass of 83 kilograms. Jupiter's acceleration due to gravity was 27 meters per second squared. So 2,241 newtons was her weight force. Now, obviously, her mass stayed the same. On our final page, we look at, not our final page, on Newton's second law page, it is the relationship between force, mass, and acceleration. F equals ma is the formula we get from Newton's law. And we find out that force and acceleration are directly related. So if you keep the mass the same, then the force is going to have to do something. The force can increase, and that could increase the acceleration. If we keep the mass the same and you decrease one of those, you decrease the other. So they are directly related. And so what we could say the relationship between acceleration and mass is an indirect relationship. You might hear it also written as indirectly proportional. So if force is kept constant and it had to increase the mass, then the acceleration would actually decrease, or you would half it, right? If you doubled the mass, you would half the acceleration. So mass goes up, acceleration goes down. Now, on the other hand, if mass decreases, acceleration goes up. So something with a smaller mass will accelerate easier, is what that's saying. And the basic equation that you could sum up Newton's second law is F equals ma, or the net force is mass times acceleration. Net force is mass times acceleration. And we study when forces are balanced and unbalanced. So force is mass times acceleration, or net force is mass times acceleration. And like I was saying, we study when forces are balanced and unbalanced. When net forces are balanced, there's no acceleration. When they're unbalanced, there's acceleration. The net force is really the sum or the combination of all the force vectors. Force 1 plus force 2 is net force. Well, what if they're going in opposite direction? You have a positive 5 and a negative 6. Well, the net force, or the combination, the sum of that's a negative 1. You do have to know when we're talking about mass and weight, there's some differences. And I'm going to go ahead and include volume in that. The force of an object, or the force of gravity on an object, is your weight that's measured in newtons. Your mass is the amount of matter object, that's going to be in your kilograms. And your volume is going to be in liters. That's how much space the object takes up. Now, the only thing that varies that we talk about was weight. Weight's going to vary depending on the amount of gravity affecting the object. Mass does not change. All right, Newton's third law states that every action has an equal and opposite reaction, or really that forces come in pairs. So for every action force, there's an equal reaction force. It just goes in the opposite direction. So let's do some examples of action reaction forces. If you push on the desk pushes back on you. When the car pushes on the road pushes back on the car. And likewise, when a bird pulls on the worm is actually pulling back on the bird. Three more examples of Newton's third law. Be a swimmer kicking off the wall, and the wall pushes back on the swimmer. There's a rocket that pushes down on the air pushes up on the rocket, and if a car is driving down the road is pushing back on the car. In this next example where you practice third law, you're finding the magnitude and direction of the reaction force. Well, it has to be the same magnitude and the opposite direction. So if they tell you there's an eastward push of 20 newtons, that means there's a westward push of 20 newtons that's going in the opposite direction. And three examples here on the bottom. A tennis ball pushes on a racket pushes on the ball. When someone's playing pool, the cue ball is moving and pushes the 8 ball, but the 8 ball also pushes on the cue ball with an equal magnitude but opposite directional force. When a golf club strikes the ball strikes the club. All right, first law, second law, third law. Can you find the difference between them? First law is going to be law of inertia. Second law is F equals ma. And third law is going to be action, reaction, force pairs. When a car runs into a post, the passengers continue to move forward. That's because of the first law. The passengers have inertia. They have a tendency to keep going forward. When you stand on a skateboard and you push back on the wall, you go forward. That's Newton's third law. Those forces come in pairs. It takes 4 times more force to push me at 2 meters per second squared on a skateboard than a child. That's the relationship between force, mass, and acceleration. That's the second law. When an inflated balloon is released, you let it go and it flies forward. That's the third law. If I pull a tablecloth out from under a place setting, that's like the magician pulls out the tablecloth. That's the first law because the dishes have inertia. When I'm standing at a stoplight, my car gets hit from behind. My cup of hot apple cider that I just put on the dashboard falls off the dashboard and it lands on my seat. Ow! If that happens, that's because the cider has inertia. It wants to stay where it's at. So that's the first law. A guy breaks his hand when punching the wall. Third law, the wall punches his hand. Your car does not accelerate as well when you attach a trailer with a motorboat. You're adding more mass, so that relates to the second law. When I quickly pull a produce bag off of the large roll, the roll does not move. That is the first law of motion. Good luck on the test. God bless you.